Alright, this video is going to talk about exponential functions. And the first thing we want to do if we're going to talk about exponential functions and what the difference is between that and what we know, let's talk about what we already know. More than likely you've studied linear functions. Linear functions just mean that as x goes up by 1, right? Notice here we're counting up -2 to -1, -1 to 0, so as we increase by 1. For linear functions, we go up by the same constant amount every time. We usually call that the slope. So notice the y values here are going up by 2, right? To get from 8 to 10, we go up by 2. So again, we get this idea that, well, we go up for y, right? We go up 2 every time that x, right, went up 1. So we get this idea of slope, right? So +2 to +1. So then we can say that y equals the slope of, right, +2 times x, so that every time x goes up 1, right, if this increases by 1, we multiply by 2. But then we also notice that when we plug in 0, right, 2 times 0 would have been 0. But notice we get 6, right? When we plugged in 0 for x, we got back 6 for y. So we also needed what was called the y-intercept, right? We had to add on a number so that when I plug in x as 0, now we add 6 and we get back exactly 6. Or when we plug in 1, right, 2 times 1 is 2. Plus 6 is 8, right? So we get all the right x values and y values all matched up. Well, for an exponential function, that's going to be a little bit different. So notice we're still going up as we kind of go along here, right? +1, +1, +1, +1. We're still going up by 1 on those x values. But notice on the y values, we're definitely not going up the same amount, right? Every time we go up. 1 to 2 would only be +1. But 2 to 4 was +2. We're going up different amounts every time. Well, and that's because for exponential functions, we're no longer adding the same amount. What we're really going to do is we're going to multiply. 1 times 2, right, would have been 2. But this 2 times another 2 would have been 4, right? And if we actually went backwards a little bit here, right, 1/2 times 2 gave us 1. Or 1/4 times 2 gives us a half. So we're going to take 2 times 2 times 2 times 2, or basically 2 times itself over and over again. And that's why we say these are exponential functions. Our variable is no longer just multiplied by the slope. We now have some number, right? Some base number, we call it, a base, that's raised to the, right? It's raised to the x. Whatever x would be is going to cause these y values to happen. So x being 0, right? 2 to the 0 power would have been 1. 2 to the first power would have been 2. And 2 to the second power would have been 4. And you'll notice even the negatives work, because remember that 2 to the -1 is actually 1/2, right? So at -1, we got back a half. When I plugged in x was -1, we get back that half. Now, you'll notice that the graphs of those, again, are going to look a little bit different as well. We'll talk a lot more about the graphing, but you'll happen to notice when we're going up, since we're not going to go up the same amount every time, what's going to happen is we're going to end up with this sort of curve going on, right? Because every time x went up 1, the gap between the previous point and the next point gets a little bit bigger, right? We go up a little bit, but then we go up a lot, right? And then we go up a lot more when we're graphing this thing. So it keeps getting farther and farther apart. Notice over here at the right, we have that same idea going on. 3 times 3 would have been 9. 9 times 3 would have been 27. Or if I took 3 to the x, right, we're getting all those powers of 3, right? 3, 9, 27, 81. 243 is really 3, right, to the 5th power, right? Now notice there though, I'm only plugging in x as 2 here, but I needed 3 to the 5th power, right? We're off just a little bit. Our numbers didn't start, right, in the right spot. So kind of like up top where we needed that +6 to offset everything, we can have an initial value, as we call it, that multiple out in front, a. So what I'm going to say is, well, 3 to the x is helpful. Well, what about if we maybe threw a 27 in front of here? And the reason I came up with that is I looked right here at this one. If I said 3 to the 0 power, that should give me back a 1, right? But 3 to the 0 times 27 Well, 1 times 27 should be 27, right? So when I plugged in 0 for the exponent, I got back 27 for the y value. And if you check any of those other points, they should work as well. Feel free to stop the video and plug in 1 or 2 or -2 into that x and see if those don't work out to give you the correct values, right, for your table. Now, as I mentioned, the most important thing we're going to do in this video is really do some graphing. And the easiest way to kind of get used to what these graphs look like is just to make a table. So I'm very simply just going to start plugging x values in, right, and make ourselves, oops, 3 to the first is 3 there, a table. So again, I'm taking my x value, I'm putting it up in the exponent. 3 squared would be 9. 3 to the third power would have been 27. And again, 3, this base number, right, from up top here, to the fourth, right, 4 being x, right, would have been 81. Now I'm not going to be able to plot all of those because they got pretty big pretty fast. And that's the idea with an exponential function, is they're going to get very large very quickly. But at 0, we got back 1. When x was 1, we got back 3. And when x was 2, right, we got back 9. So 4, 5, 6, 7, 8, 9, way up here. Notice again, we went up 2 points, then we went up another 6 points, right? And we're going to go up even more to get to the next one. We'd have to go all the way to 27, right? 3 times higher than that. So again, spreading out, notice that little bit of a curve going on there. And you'll notice the curve even more when we talk about negative exponents. Right? Remember that negative exponents make fractions. So 3 to the -1 is 1/3. So when I go over here to -1, notice I'm not even passing the x-axis. I'm going to just be at 1/3, right? Just a little above the x-axis. And same thing at -2, we're at 1/9, even closer to the x-axis. So we're just getting smaller and smaller numbers, really close to that x-axis, right? But notice I'm never going to quite cross there, right? Even at -2, we're at 1/9, which is similar to here. Well, at -3, we would have been at 1/27th or 1/81st when we were at -4. We're not getting back negative numbers. We're just getting back tinier and tinier fractions, right? Which means that as we go to the left, what we end up getting is what's called an asymptote. We get a line that we're going to get infinitely close to, right? Right now it's 0. We're going to get really close to 0, right? But no exponent, right? No x value I could ever plug in would ever make 3 times itself, right? Over and over again into 0. That'll never equal 0. And it will never, right, be less than 0 either, right? Which is why we say that the range, right, all the answers we get back, the y values, right, that we get back will always stay greater than or equal to 0. Sorry, and never equal either, right? We said not equal to. So again, they'll always be greater than 0. We can plug in anything we want, right? The x value, or the domain as we call it, right, can be all real numbers, right? That's what that R with the double bar there is. That's all real numbers. But we'll never get answers back, right, for the range that are ever negative or 0. One of the easiest points to remember before we move on to a little bit more work here is just to remember that the point of interest, a really easy point to find, is usually when x is 0, right? And it just happens for this one, well, hey, 3 to the 0 power is exactly 1. But typically plugging in that x is 0 is a great idea for exponential functions because it's easy to find that first value, right? Where we're going to be right on the y-axis, right? When x is 0. Pretty easy point to find. So let's start with that on our next example. Notice we've still got 3 to the x, but now we put a 2/3 in there. So I've got all my answers from the previous screen for 3 to the x, right? 1/9, 1/3, 1, 3, 9. But now what we're going to do is multiply by another 2/3, right? And 2/3 times 1/9 is going to be 2/27, so even smaller, right? If I go over to -2 here, I'm going to be below that blue line. Let's get a whole lot of answers really quick here. If we multiply by 2/3 every time, this is going to be 2/9. 1 times 2/3, right? 3 to the 0 would have been 1. 1 times 2/3 is 2/3. So notice on that y-axis, I'm not even up at 1. I'm just 2/3 of the way up there. 3 times 2/3 will be 2. 9 times 2/3 is 6. And then after that, we start getting numbers, right? It's 2/3, not 1/3. There. So again, I'm not going to be able to plot all of these, but again, we said when x was 1, y was 2, right? We get the point 1, 2. So at 1, we're here, where we used to be up at 3, right? Now we're down at 2. Where we used to be way up at 9, now I'm at 3, 4, 5, 6. Right about here, right? This would be the point 2, 6. Whereas, again, on my original graph, right, this would have been way up top there. In fact, off our graph, where we used to be at 2, 9, right? Now we're at 2, 6. So that red line is just going to coast right underneath the blue one, right? Right underneath there. And notice as we move to the right, that gap between the blue line and the red line gets bigger and bigger, right? Right here it was pretty small. Right here it was really tiny, only 1/3 there, and it gets tighter out to the left. We still have a horizontal asymptote, right? At y equals 0, our exponent will still never turn our answer negative or into 0. But what happened was our graph shrank. It's a shrink of a graph. The red line is definitely closer to the x-axis. It's almost like we pushed down on that blue line, right? And we shrunk it downwards, right, to where the red line is. Again, comparison words are very helpful. Most of our graphs, again, you can graph that simple 3 to the x like we did with this blue line, but most of the graphs we're going to talk about will either be a shrink, a stretch, or reflection. And they're according to whatever that front number is. I'm taking all my values, all my blue values from my blue line, and I'm multiplying by -2 this time. So 3 becomes -6, 9 becomes -18, and so forth and so on. 1/3 would still become -2/3, right? I'm just going to multiply by -2. Same thing, -2/9 when I multiply by -2 times my 1/9. So notice our numbers are actually getting bigger this time. 3 times 2 was 6. We just happened to also become -6, right? So this time what happened to our graph? 1, right? What used to be 1 here. Well, now I'm at 0, -2. I'm down here. So we definitely stretched, right? Our numbers are larger, but they're also much lower. They're also negative. So it's almost like we took that blue line and we flipped it over that x-axis. So we also reflected it. We stretched it to become larger numbers times 2, and we reflected by negative. So if you multiply by a negative, that's a reflection, right? It's because we multiplied by the negative, but we also multiplied by a number that was greater than 1, right? Our number that we multiplied was greater than 1. So that's a vertical reflection, a vertical stretch. If you talk to your teacher, if you have any questions about those, make sure you read some examples out of the book as well. We'll talk more about the applications of exponential functions in a minute here. So feel free to watch the second video, and otherwise, have a great day.